MATLAB.
So the input to the function are the number of half cycles, or?
Oh, it reads in the file and it calculates everything. It calculates how many
What do
half
you, what do
cycles
you,
there are.
what do you read into it?
You just give it the stress file. So I can show
Stress
you
is a function
an,
of,
an example of
yeah.
what happens. Is you go and okay, so open my documents, and then rain flow. So this is just the cycle counter. So it's just a function, and all you're given it is the stress. So the stress data is like 1, 10, 5, 6. These are the peaks, right? Because it's 1, then 10s, and go back to 5.
Oh, so you just give it the peaks. Yeah,
Yeah,
oh,
but
okay.
you can actually, it's written.
So that's the input, yeah. Okay.
But it's written where it will take any stress data and it will calculate the peaks. So I just gave it a stress file of this, but in the real, because you're just grabbing this COMSOL file, right? This stress file. Some of the data points are not going to be peaks.
Yes,
so
yes.
the program already calculates. It goes and calculates the peaks, and then it will run through the whole rain flow method, where it will figure out the half cycles, and then it'll, for the min
Very
max
good.
and everything.
Yeah, you developed it yourself?
Yeah.
Excellent.
Kind of took some time, but
Now I don't have to teach rainflow method.
yeah, like you can use this. This is great. You can use this on homework. You can use this to generate rainflow problems.
Yes.
It works pretty well. I've tried all these different situations where how the flow keeps going.
Yeah.
And it drops off. I drop off markers essentially. So then the next rain flow will stop at those markers. So.
Good job, Dan.
Yeah, I mean the code it's just looping through a bunch of stuff.
And I guess this worked better than the FFT method, fast Fourier transform.
I don't know exactly why it was messing up with
There was,
that,
some glitch in it, I think.
Something. But yeah, I just loop through and then find the maxes and stuff and then add these markers. And then essentially when it's done, it has the whole, the mean, max, and alternating.
Yeah.
So in this program, so the nice thing is the students can see like, okay, this is how this one function works. So I have them kind of go through it and try doing this by hand and then checking that the program works because and then the next program is the modified endurance limit.
Yeah. So before you go, so they have the SXX, SYY, SXY. So they have to convert it to two principal stresses.
Yeah.
And then apply the rain flow to each one independently.
So it's all in the program though. The program here. If I open up the next file,
your program will do the conversion.
This one file will run all of this.
Yeah. So.
I just wanted them to see what the files were doing.
Yeah, because we discussed it and we decided that's the best way to do it is just convert to principles.
Yeah. See, the program will convert the stress file. So this is the main file that you run. You run this. What is it called? Rain flow, fatigue, principal stress. You can see it down here. Principal stresses. And so you have to give up these parameters, your yield strength, your yield cycles, the ultimate, and then it will call this modified endurance limit. It will calculate the endurance limit that you should use based on design parameters. And then you essentially, this is where it will take in the stress data. So all you have to do is go like this, import the data. So I would go and select my where is it? I would just select this data and say open, and it takes some time because there's a lot of data, but because that will come in as sigma x, and that will just make it and then it will just use this SS. So it just goes through and see like it has component cycle node. That's it puts it in a 3x3 matrix or a 3-dimensional matrix. And then it calculates the principal stresses, and then it takes those principal stresses and it goes through and it just loops through this function. That would be if I wanted to see, it gives you the truncated and it gives you the file, and then you can just save as sigma x. And then now you have this stored in here. So like when they run this, they have to input the files, and then all they have to do is say run, and they can just run this file. So it just calls the rain flow counter, that's that other function, just by giving it the principal stresses.
Yes.
So
And this for one node only, right? So
yeah,
you,
so
you
it's
selected
looping through
one
all
node.
the nodes. See, looping through the nodes. So it just does one
So
node.
we'll do one node at a time. So you will
Yeah.
have like a map of damage parameter at the end of the day.
Exactly. So
Okay.
we'll calculate this damage and we'll put it into this array for all the nodes, all the damage it has,
right.
and then it will do this graph. So
And then it will plot it for you.
yeah. So if you go back to here, the end plot is so for this example, let's zoom in.
The distribution of damage
Yeah.
per cycle.
Yeah, so for this one, the only one that had the only one that had enough damage to get over the endurance limit was this point here because it had the highest contact stress.
Yeah.
But this was actually a safety factor of 1.1, so this is good. That means that you didn't yield, but you actually don't have infinite life. So you and because your life, once you're on the endurance limit, right? Once you have anything that's above the endurance limit, your damage is going to be here. You're going to have less life than NE. Which is, so that's why you can't really get 10 to the 7, 10 to the 8, unless your NE is all the way up there, right?
Right, right.
So, so then, so I don't know if they should be designing for infinite life or design for very close to the NE value of cycles.
Well, for the connecting rod, I think it should be like infinite life, but at least so they can get at least like 1 billion cycles minimum for the connecting rod. But this is really a good illustration of how we calculate the damage per cycle and how we can control it.
Yeah.
And in fact, it can help you do optimization. Once you identify the critical points, you can optimize a little bit more.
Yeah, exactly.
If there's a cost function or penalty function, if you add more material, then it will cost more, but then at the same time you can improve the lifetime. So there's some trade-off issues here.
Yeah, so if you wanted to design for like 1.05 safety factor or something like that, then this would be a problem because then you don't have infinite life and fatigue, and so then you have to write the optimization so it takes into account the fatigue as well.
Yeah.
It's not just the stress analysis now. So the way this works for the endurance limit is it modifies the endurance limit based on. So this is where I explain it. It modifies it based on just Shigley's design book has designs based on the size and the reliability, and I can show you the M file real quick. Open this thing. There we go. So it's just calculated. So you start with taking, half of the ultimate strength. That's the endurance limit, and then you can surface finish has a factor, right? So you have. And these are just straight out of the design book that you can use. So the students can change this. Like if they want use, like machine is probably connecting rods probably more machine, right? Versus, but if you hot rolled or depending on what you're looking at, and then the size factor for this, I assumed it was essentially axial loading.
Yeah.
So for that it doesn't have a size factor, but for this it has a factor for axial loading, and then a temperature factor. So if your engine runs really hot versus really cold, then that has a factor on the connecting rod. And then reliability, this is just based on their reliability factors. So if you have, if you want 99.99% reliability, then your endurance limit has to be reduced, so that's why this factor. And then just the standard, Ka, Kb, Kc times the endurance is your modified. So now they can add in reliability, which some people were like, oh, how do I do that kind of thing?
Right.
So
We can also ask for reliability if we have the SN data that has actually Y-ball distribution. The SNP, that if we can generate that, then we can actually compute the reliability of design for a given number of cycles.
Yeah, because these charts were based on statistical data.
Yeah. But if we have statistical data, then we can use the information in the class that we learned, and then we can actually compute the reliability for a given number of cycles.
Exactly. So that's what this design book did. They took their own statistical data, and that's why these factors come from that.
Yes.
And all these programs are embedded in your PDF file?
Yeah, they're in the PDF, but you just have to click on the...
Yeah, that's the beauty, is that
nice.
Everything is kind of integrated.
I mean, you put an enormous effort into this.
Yeah, he worked for a whole quarter. In addition to the quarter of the class itself that he worked on.
So then... So that's essentially the whole fatigue analysis. And then you could calculate how many life cycles that you want to have it run and all that. And then the fracture mechanics, we let them do that using a Paris law.
Okay, so for the fracture mechanics, I guess we identified kind of the critical zone from the fatigue analysis. We have the maximum damage. We could actually put a crack in there and then see how far it propagates with the Paris law, right? Okay.
Yeah. Yep. And so they're just encouraged to try doing MATLAB program or something.
So that they will do by themselves. So they can get that and get the stress amplitude and then the Paris law, and then they propagate the crack and get the critical size for fracture and all of that.
Exactly.
Great.
So this is the design optimization. So right now it's just on the stage of like do it yourself. Like you were saying, the mentality is you can do the load analysis, the preliminary analysis here. Let me just expand this. And then you can essentially start going through the FEA, the 2D FEA analysis, and then do fracture and fatigue, and then see like, is this feasible? Have I gotten to an optimal design? You can modify. If no, okay, then change the dimensions, change thicknesses, change height, width of the beam, and all this other stuff. And that's where you can do parametric sweeps, like you're saying, where you change the thickness and then you parametrically sweep through, and you can see, oh, this design curve shows, oh, this is good, I want to be here. But you could also do is you could try to write a MATLAB link console to actually do a design optimization function and take an. So I didn't get time to do that.
We're going to do that in the fall when you come back.
I can do that, yeah.
Yeah, because we have an optimization, this swarm optimization, and I think you have all of the data now to be able to do it.
Yeah. So yeah, this should work out well. But I mean, you can at first have them, just the students do it themselves, and then say, oh, by the way, now run the program and see how close did you get to the optimal design just by hand.
Yes.
So then, now this is so once you're done with that, the final thing is like, oh, I have my optimal design. Now I want to say like, okay, now I want to make a real version of this. Like right now I just did a 2D analysis. I mean, there are only two plane forces, so like it makes sense. But now I want to see like what a real part is going to look like. So now you go into the Solidworks model and you make a real 3D model of this. Yeah.